Hello, thank you for joining us. Welcome to this webinar event. You have tuned into one of many such webinar events that is part of the professional development program that is brought to you by Texas Instruments Australia as our ongoing support for teachers in the classroom. This evening's webinar is Teaching with Technology. Our presenters are Peter Flynn and Shelley Cross. Can I tell you, my name is Brian Lannon. I will be your host for this event. And can I tell you just a little bit about the Teaching with Technology? It is not just a skill set, it is a mindset. So fasten your seatbelts and as the presenters in this webinar take you through a visual journey through mathematics. The brain, if you are interested to know, processes visual images up to 60,000 times faster than text. How about that? Engagement is 58% higher on Instagram compared to Facebook. Well, I'm on neither, but okay. Now, our brains are pre-wired to never forget a face. I see what you mean. It's a part of our vernacular. Powerful visuals increase engagement, are more memorable than text, and can be used to improve student understanding of mathematical concepts. From Year 7 to Year 12, teachers can use TI-nspire teacher software to help illustrate an enormous range of mathematical concepts using powerful visuals. I expect you've already read that because you will have looked at the brief for this webinar before signing up. So there it is. It's a mindset. And it's also a learning style. I know for a fact that my learning style is definitely much more visual than anything else. Never forget a face. But that might be an appropriate segue to introducing one of our presenters this evening, Peter Flynn. Now, Peter will be presenting second this evening. He's a T-Cubed instructor. Has been an educational technology with TI Australia for quite some time now. Mathematics educator for over 20 years, and his speciality is the effects of CAS, computer algebra systems, on teaching, learning and assessment. And the best of all, he shares this expertise generously with colleagues both here in Australia and also abroad. Good evening, Peter.
Good evening.
And good to have you on board. As also, Shelley Cross. We'll actually be hearing from Shelley first of all. She's also a T-Cubed instructor and teaching at St Hilda's School on the Gold Coast. Good evening, Shelley.
Hi, Pete. Hi, Brian.
Great to have you with us this evening. Teaching for 30 years, over half of which in Australia, and quite a proportion of that as a teacher mentor. So once again, you're getting teacher trainers here, passionate about students learning and understanding the concepts rather than just learn the facts. But how does it work? And using the TI technologies as tools to assist this. She's also used them, well, right through from the early TI-83 up to the current TI-nspire calculator, and then the app. Now, Shelley, when you refer to the app, are you meaning the apps that are on the Apple?
Yeah, that's the TI-nspire app, CAS app, which is a program app you can use on an iPad.
I have seen that, and it's really good stuff. Or the set of apps, really very, very useful. And I see that you've added to that with an iTunes U course, which I don't have access to because I'm not in the iWorld either. Windows is my thing, but for those people using that, I think that would be a good thing to tune into, which includes a set of videos helpful for that. So without further ado, I'm going to swap across to our first presenter this evening. That's Shelley. We have Shelley's screen on board. Can I just suggest, if you have all the other WebEx stuff around the edges, and you want to see exclusively Shelley's screen, there is a double, if you put your mouse over it, there's a double cross where you can maximise. I think if you just click on it, it'll maximise. Yeah, double click on it, it will maximise, and you can see exactly in large screen detail what Shelley is showing us. Thank you, Shelley.
Hi everyone. What I'm planning on doing tonight is to step you through a series of building little animations, I suppose, for want of another word. So I'm going to build them from scratch. Hopefully you can follow along as I'm going through what we're doing. So I'll step out all of the key sequences as we're going. If I go too fast, send a message to Brian and he'll tell me to slow down. If I'm going too slowly, likewise, speed me up. So hopefully I'll get the speed right and we'll all be able to follow along. So the first thing we're going to do is build a right-angled triangle, measure the sides of the triangle, and then prove Pythagoras' theorem. So we'll do that by starting with a line. So we hit the menu button, point to line, and we want a line. So we want this line to go somewhere along the bottom of the screen. So click on the bottom of the screen and just drag the finger along so that the line is quite long, and then click to place the line on the screen. We don't want that line tool anymore, so we're going to hit escape to get rid of the line tool. At this point, we also need to put a point on the bottom of that line because it's going to be a triangle. So we'll go menu, points and lines, point on. Go over near to the line, click once to select the line and once to put the point on the line, and escape to get rid of the tool. Now we're going to put a perpendicular line at the left-hand point. So we'll go menu, construction, and we're going to construct a perpendicular. Click on the point and click again to put the perpendicular line down. What we can do now is get rid of the tool, so escape, come back to this line, and we can drag that line up towards the top of the screen to make it a bit longer. Now we're going to put a point on that line as well, so that we've got the third point for our triangle. So menu, point to lines, point on, click once to select the line, once to put the point on the line, and then escape. Now we're going to join these points to make our triangle. So menu, point to lines, and we'll use a line segment. So click on both of those points to put the line segment down. Now because we want to actually measure the lengths of the three sides of the triangles, we need to put some more line segments on that triangle. So we'll click on the same point again, back to the point near the right angle. So that's got a line segment on top, and again on top. Now the reason I'm doing that is because I'd like to measure the length of those lines. And if I measure the line, it'll measure the whole line if I haven't actually put the segment on top. So I just want to measure this particular bit of the line here. So let's measure the sides of those lines now, the length of those lines. So we go to measure, menu, measurement, and length. Touch the line we want to measure, which was not what I wanted to do. Go back, escape. Menu, measurement, length, and place the measurement down. Seem to have lost my line segment. I'll measure the length of that line there between the 2 points and measure the length of this line between the 2 points. Right, so hopefully we've managed to measure the three sides of the triangle. Escape to get rid of the measuring tool. We could label this triangle, but I'm not going to bother with that at this stage. What I'm going to do now is look at the three sides of the triangle, and I'm going to assign variables to these three lengths. Hover over the text, which I'm not sure what yours will say. Mine's 18.5. Right click, and we'll store this. And I think we're going to store this as C. So I've stored that length as C. Let's store the base. So right click, store as A. and the perpendicular height, right click, store as B. Store that as B. Right. My three sides of my triangle are now stored as A, B, and C. So what I'm going to do now is put the formula for Pythagoras in the right-hand corner of my screen. I'm going to use a text to do that. So menu, actions, text, and I'm going to type in there C equals the square root of A squared plus B squared. Escape to get rid of that text tool. We now want to calculate what the value of C is. So right menu, actions, calculate. Oopsies, not like that. I'm calculating this expression. So I want to calculate C. It prompts me to say select A, so I select A. This was my variable A. Select my variable B and put the value on the screen. And we can see there that the values are the same. So what we've done is we've drawn the triangle, we've measured the hypotenuse, and then we found that through the calculation, A squared, the square root of A squared plus B squared is actually equal to the same value that we've got on our screen. So that's the first one. How am I going for pace, Brian?
Yep, I reckon that's good. I'm just wondering, and I'm going to send out a survey shortly, how many people have tuned into this as a pure introductory thing, or are they zooming ahead with the technology? I'm going to send out a survey shortly because it just crossed my mind. I wonder how many people are aware that this is a geometry page. A lot of people, when they
mentioned that at the start.
Yeah, when a lot of people first switch on their calculator, all they see is they generally go to the calculator page. Also worth stressing that this is the non-CAS that we're using here. So this is not the computer algebra system version. Is that the go?
Yeah, but the CAS and the non-CAS will do the same thing in this particular.
Okay. Yep. So I'll send out that survey just to see where people are with this. But of course, the page types also include, graphing and spreadsheet data and statistics and so on. I have been putting out some little messages that'll pop up in the chat box. So I'm hoping people are monitoring that. When you see that speech bubble pop up at the bottom, just click on that and you can read the chat that I'm sending out. But also, please talk back. Ask us some stuff. Let us know how it's all going on. Thanks, Shelley. Yep.
So sorry about the geometry page. I forgot to mention that. The nice thing about this, though, is if you hover over the point, you can actually slide this point along the line, and you can see live that as the length of the base is now changing, so is the length of the hypotenuse, and the calculation changes as well. I think this is quite a good little animation to get kids to build up, and because I think it's quite powerful to show that visual picture of Pythagoras. Right, so on to the next one. So our next one we're going to look at is the Cos ratio. So we'll do a similar sort of thing. Build up the triangle, put in some calculation in the text boxes. So we're going to insert another geometry page. So we'll hit Doc, Insert, and number 5, Geometry. So we'll start with a fresh geometry page. We're going to build another right-angled triangle. So pretty much the same thing that we've just done. Menu, Points and Lines, Line, point on the bottom of the screen and drag the line across the screen. Escape to get rid of that line tool. Menu, Points and Lines, Point on. Put a point on the line again. Let's put the base of the line there, and let's make it a different color this time. So we'll go Menu, Points and Lines, Segment, and put the line segment between those 2 points. If we go onto that line segment now and right-click, you'll see that we've got some things we can change. So we'll change the color of that line segment, maybe to red, so we can see it clearly on that triangle. So now as I move this point, I can see the line segment is between those 2 dots. Let's construct the perpendicular height. So we'll go construction, perpendicular, click on the point and click again to place that line there. And we can drag that up to make it longer. Escape to get rid of that tool. We'll put a point on the line again. So menu, points and lines, point on. Click once to select, click once to place, and escape. And we'll put a line segment, points and lines, between those 2 points. We'll also put a line segment for the hypotenuse. So we can change the color of this line, maybe to green. Right, so here's our right angle triangle. We could measure that angle, but we know it was constructed as a perpendicular line, so we don't need to measure it. What we're going to do is we're going to measure the angle in the bottom right corner. So we'll do menu, measurement, measurement and angle. Click on the point to make sure that the angle that you're measuring is in the center. That angle at the moment is 49 degrees. So what I'm going to do now is measure the length of the adjacent side and the hypotenuse. So we'll do menu, measurement, length. We'll find the length of the adjacent side and the length of the hypotenuse. So what we've got is the angle in the triangle and the hypotenuse and the adjacent. So let's put a formula there now. Menu, actions, text. And the formula that we want to do, we actually want to divide the adjacent side by the hypotenuse. So let's use control divide to have a fraction, and we're just going to type adjacent divided by hypotenuse. So what we're intending to do here is to set up a little animation that when we drag the point, it will automatically find the ratio of adjacent divided by hypotenuse for us, and then in a separate text box, find cos of the angle, and they should be the same. So we'll put cos, and the angle, we'll probably call the angle capital A, so let's cos of A. Now we need to define these, put some variables on these lines, so assign some variables. So escape to get away from the text box, and let's right-click, store this. So we need to make sure it matches with our formula. So this is hypotenuse. We'll store this here as adjacent. And we'll store this angle here as A. Oh, sorry, what happened there? Adjacent, and then we might just move this out the way and store this one as A. So all that remains now is to do our calculations. So to calculate, menu, actions, calculate. This is the expression we want to calculate. So select the adjacent side, select the hypotenuse, and put the value over here. Now let's evaluate cos A. So evaluate this expression, select A, and put the value here. So we can see that the cos of angle A is the same as adjacent over hypotenuse. For the sake of some small aesthetics, I think it probably makes sense to just put an equal sign over there. And again, as I drag this point, get rid of my tool, as I drag the point, the angle size changes, the hypotenuse and adjacent all change, but we can see that the ratio stays the same as the value of cos A. So that's our second one. Hope everybody's keeping up and this is being useful. Of course, you could do this with sine and tan. The only thing you would have to be careful of if you're in the same document is that you don't assign the same variable to more than one quantity.
And of course, the other thing worth mentioning is all of this work, you've got the page in degrees settings,
Yeah.
where the original default setting of for new players, it would be sitting in radians, and that's indicated up the top there. Yeah.
So you could do this in degrees or radians, changing the page into changing the settings in the page, doc, settings and status, and change the document settings.
And that's where it is. Yeah. I'm only mentioning that because that one came up in a class I was teaching today. I had a new group of students that I was teaching, and they were looking at their technology and thinking, hang on, how do I adjust this? So that's where that's found. Often people are often looking for that. Meanwhile, in the background, you can see that I've opened that survey on the beginner, or some experience or regular user or expert. Your familiarity with the use of this technology. So thank you for that. So the poll is open now and will be for another 3 minutes and 15 seconds.
The one thing that's also worth mentioning about changing the settings, degrees and radians is that I'm sure people are aware, but I came across a teacher yesterday who actually didn't know that if you're doing graphs, you actually have to change the settings from degrees to radians in a graphs page. So the
Correct.
calculation pages,
that's a good point too, because the graphs will automatically default to radians.
Yeah. Yep. So to change your graph, you actually have to make sure that you've changed it in the graph page itself into radians or
yes.
degrees or radians. Yeah. Right. So I hope that's going well. Let's look at something with circles. So what we're going to do is open up a new geometry page. So we'll go Doc, Insert, and Geometry. So I'm going to look at the geometry circle theorem, the one that is the angle at the center of the circle is equal to twice the angle on the circumference, subtended by the same arc. So we'll draw a circle to start. Menu, Shapes, Circle. Click on anywhere in the screen to put the center and drag slightly outwards to create a circle, and click to place the circle on the screen. There we go. Get rid of the circle tool. So what I'm going to do now is I'm going to put 3 points on the circumference of the circle. So menu, points and lines, point on. I'll put one up here. So click to select the circle, click to put the point on. Click to select the circle, click to put the point on, and click to select and click to put the point on. Get rid of my tool. I'm going to join all of these points with line segments. So menu, points and lines, segment. So just click to join all of the points and get rid of my tool. So now we'll measure the angles. So menu, measurement, and angle. So the angle at the center at the moment is 90.6 on my diagram and 45.3. There we go. So generally you can clearly see that the angle is twice the angle on the circumference. The nice thing about this is as you drag the points around, it still stays as twice. But I think it's quite useful actually putting that calculation text box in. So we'll text, calculate, and what we're going to do is say twice angle C, so 2 times angle C is what we want to find out. So now we need to assign a variable to the angle on the circumference because we're expecting the angle at the center is double the angle on the circumference. So we'll store this angle as C. To calculate, oopsies, we're going to do menu, actions, calculate. The expression we want to calculate is 2C. And there we go. It's equal to the angle at the center. Again, one doesn't have to, but it makes sense to put the equals there. Oopsies. So I quite like this. My intention for these diagrams that we're drawing really is something that you would teach the students to do, and the kids would become quicker and quicker. They'd be able to build things themselves and then do different things themselves. So moving the angle shows the angle at the center is twice the angle on the circumference.
Yeah, it's the sort of thing that I find students love doing, and they're really happy to engage with. Of course, it's not rigid geometric proof, but it's pretty convincing, isn't it? When you can move something dynamically and see it all happen, and very easy to construct, as you've just shown us.
And the visual nature of the whole thing does just peg it into their brain. Certainly going through the rigorous proof, that's a different thing altogether. But for them actually to remember what these connections are, I think this visual picture is very powerful. Yep.
I've used this, what you're showing here, I've used this a lot at Year 10, and as I said, kids love it. It's easy to just make up a few worksheets. There are that sort of thing on the Texas Instruments Australia website with worksheets. Just give it to the students, off they go. And I'm so pleased that you've shown us how to build these constructions, because that's what the students really need to do, rather than take just a pre-made file. I think building it is so much more powerful.
I think it also makes them think about what the connections are that they're looking for, because much as this is an easy little formula to put in there, it actually presupposes that they've thought about what they think the relationship might in fact be.
Yeah.
So maybe, Brian, I'll just do one more.
Okay, yep.
Just a cyclic quadrilateral one. So insert again another geometry page. Insert another circle. So shapes, circle. And what we want is 4 points on this circle. So point and lines, point on.
I love the way the little tool pops up in the top left-hand corner to remind us what we're doing.
Yeah. When you try and do something and you notice there's still a tool there, that's when escape is needed.
Correct. Yep. Switches it off. Yep.
Right. So now we'll just join all of those points on the circumference of line segments. So we'll go from around the circle. Okay, get rid of that tool. So what my intention is here is to add the opposite angle. So I need to measure to the opposite angles and then put a text box in to add them. So I'm going to go menu, measurement, angle. So I've got that angle and this one here. And then my text will be, I'm just going to call the one A1 and the other one A2, and I'm going to add them and see what happens. So let's assign this one, right click and store it as A1, right click and store this one as A2, and then menu, actions, calculate. I also like that it prompts me what to do next. So select A1, select A2, and there's the answer. So basically showing me that the opposite angles of a cyclic quadrilateral are supplementary.
and of course you can adjust that, adjust the points in the cyclic quadrilateral, as you showed before. It's dynamic as well,
And
she still works.
Sum of the values doesn't change.
Yep.
Yeah.
Love
so
it.
I think it's pretty neat. I really do like the whole visual things. Yeah. And I'll just put one in quotes. There we go. So all of the circle theorems, as well as cyclic quadrilateral theorems, could be, as an initial investigation, developed like this. I think I spent it this year. I did it with a class of year 10s, and they absolutely loved it. They were lying on the floor like we were in the movies, getting on with exactly what they needed to do. I stepped them through step by step on the big screen so they could actually see what they were doing. But once we got about halfway through, they were able to pretty much get on with it themselves, and they were just forging ahead, not even waiting for me. I was just really helping the ones that were a bit slow get where we needed to go. So I've got quite a few of these in a PowerPoint presentation, Brian, that I'll just send to you at the end.
Fantastic. And so that will then be shared as part of the files that are available to participants following the event.
Great.
Yep, good stuff.
So I think maybe I could do more, but I think maybe we might stop there.
Well, I tell you what, keep them in reserve. We'll see what Flynny's got. What do you reckon, Flynny?
I was happy for Shelley to keep going until 2 minutes to 8.
Yeah, good on you. But we I tell you what, Shelley, we may, if we reckon Peter's stuff is not up to scratch, we'll come back to you for more of this good stuff. Because yours is proven the jury is still out on Peter's.
I think his is going to jump to another level. I have a feeling.
We have a feeling, but having said that, I think we do need to be mindful of the calculator expertise, or the TI-nspire expertise that our viewers have. And I know people often ask me, are these webinars available to watch later on? Yes, they are. They're all recorded. When you go to the Texas Instruments Australia website, and I'll type in the link for you, I'll type it into the chat box, you can actually watch recordings of this and download all of the associated files, which, Shelley, you're going to say this one here that you've just built, if you could save that so that it's not just called doc, but something, that reflects what we've just done here. And you can download this and play with it. And also the PowerPoint, as that Shelley just mentioned, you can see what Shelley's doing there. She's saving it. And so this will be available to you on the website, and often a great thing to share with students as well, I think. So that's a handy one. So I'll zap us across to Peter then. So thank you for all of that, Shelley. As I've said, it's great stuff for students to engage with. Certainly very visual, and they get into it. If student engagement is what we're aiming for, we have a winner with that. So we'll swap across to Peter. Now, what I was starting to mention before, Peter, from the poll that I sent out, we do have quite a few people who said absolute beginner with TI-nspire. So not necessarily absolute beginners with mathematics, but we do have some beginners, absolute beginners with the TI-nspire. The modal group, shall we say, were regular users, however, and a few who indicated that they're experts. So we've got the full range. And we can see your screen in lovely colour, Peter.
Thank you, Brian. So when you did the poll, I also said I was an absolute beginner. So in the remaining time, we're just going to look at some alternative ways of visualizing the nth roots of unity. Don't worry, if this is in the guise of complex numbers, there might be some skills or some possibilities that you can use in topics and subjects and year levels other than complex numbers. What I'm going to show you tonight is a little bit different to the way I was first introduced and studied complex numbers way back in 1984, where it was just essentially pen and paper, and any diagrams, of course, were on paper, static diagrams, where we would plot solutions to equations on the Argand plane, etc., etc. So this first page here is a notes page. So I've just written some text, and there's my email there if you wanted to make contact with me about this. I'm just going to skip over some mathematical background and get to the next page here, which is also a notes page. And what we're going to do is we're going to consider equations of the form z to the n equals 1. Now, what I've got here, first of all, is on this notes page, I've got a slider. And so what we can do is we can change the values of n. So menu, insert, and then slider number 5. And then you set it accordingly. Or assigned, you can do colons equals there. I've assigned f of z to be z to the power of n minus 1. And what we can do is we can use the slider to change the values of n. And this object here, this one here, and this one here, they are called math boxes. And they can be accessed by pressing Control M to insert a math box. And math boxes come with the notes application, and they are interactive and they're dynamic, so you can link them up, and we can look at quite a few cases at once. So, for example, what you can see here is when n equals 3, we have 3 roots to the equation z cubed minus 1 equals 0, or z cubed equals 1. And we've also taken or isolated the real parts of the roots and also the imaginary parts of the roots. Now, inside this math box, if I click in here, the command I'm using here is a cas command. And what I'm saying is I want Z1, and I'm going to assign that to be the complex polynomial roots of f of z. So where do you get that particular command? In the notes application and in the calculator application, in menu, if you go to polynomial tools, you'll find complex polynomial roots. And in this particular math box, what I've done is I've said, well, I want x1, and I'm going to assign that to be the real part of z1. Now, the assign command, if you look at your keypad, is accessed by pressing Control and then the symbols template. You can see a colon equals there above the symbols template, and it's in blue. So anything in blue can be accessed by pressing Control and then that particular button. And the clever thing about this is I'm sending x1 and y1 to a graphs page. So what we can do is we can plot the nth roots of unity. So we can change the value of n, and we can see what's happening to the number of roots and the position of the roots with respect to an Argand plane or a complex plane. So to come back here just to illustrate the use of the slider, we click on there, and for n equals 4, we get 4 roots. N equals 5. It's a bit messy, but believe me, there's 5 roots. This is all from the fundamental theorem of algebra. N equals 6, 6 roots, etc., etc. So this is mathematics of a different flavour. We know that we would expect students in solving z cubed equals 1 either to use de Moivre's theorem or to say, well, z cubed minus 1 equals 0, and then we can factorise as a difference of 2 cubes and get z minus 1 by z squared plus z plus 1, and then factorise the quadratic factor. And just because of time, I mean, there's probably a few brilliant questions that I would ask the students along the way that I might not get to tonight, because I also have a focus of teaching you a little bit about the machine. So if we go to the next page, what we see is we've got a couple of sliders. We've got one where we can change the value of n. We've got the angular spacing measured in degrees. Now, Shelley showed you how to do that when she was showing you the Pythagoras demonstration. It's a matter of using text and the calculate command. The formula I've put in there is 360 divided by n. You've also got the option here of showing the circle. And so for n equals 3, what we have is we have 3 solutions. You see that we've got complex conjugates. We've also got the real one there at z equals 1. And so we could say to the students, well, okay, if we increase the value of n, what might we expect to see? So if we increase it from 3 to 4, lovely, we see that we've got 4 dots. 5, 6, each dot representing a solution, and so 7, 8, and you also get an update on the angular separation. So what you could do with the students is you could say, well, okay, for the angular spacing, could you postulate or conjecture a result? And and hopefully, if they've been noticing what happens for particularly n equals 8, n equals 6, n equals 4, and n equals 3, 360 on n, 2 pi on n. So when things are moving on a screen, what you have to do is with your questioning, you've got to be able to exploit that and make sure that the students are seeing everything you want them to see. That's the partnership when you're teaching with an emphasis on visualization. So I just want to show you, if I press tab takes you to active parts of the screen. But if I now go to arrow up, if you remember from page 1.3, the real parts were assigned to be x1 and the imaginary parts were assigned to be y1. And that's the beauty of this, because what I've done is in scatter plot mode, I've now been able to exploit that from the notes page and to be able to now have these points. And so they will have coordinates which are given by the real parts and the imaginary parts of the roots. Another nice thing that you can do is you can say, okay, now I'll be a little bit quick with this one because Shelley did a really good job with line segments and measuring line segments, is what we could do is we could say, well, let's consider this to be an equilateral triangle, and we could also say, well, all right, why don't we look at finding the distance from here to here and the distance from there to there, and see and multiply them together and see what may transpire. So if we press menu, number 8 for geometry, number 1 for points and lines, number 5 for segment. I need to be really careful here. I think I've found it. And then down here, I need to be really careful. Found it. Then I'm going to press escape. Then press menu, geometry, measurement, and measure the length of that line segment. What you'll see is it's 1.73 units. It's root 3, which you could also get the students to verify with pen and paper, so it's very important in this environment to toggle between the machine and also nice pen and paper mathematics. The other thing that you can do is you can get down here and you can move it, and it jumps to this other point. This length is also root 3, or in decimal 1.73. So if you form the product root 3 by root 3, you get 3 for n equals 3. Now what I'm going to do is do some deleting. And now let's go to n equals 4. Now for the sake of brevity, I'm not going to add the line segment. But you could say, well, okay, let's make this our reference point. From there to there, you can calculate, verify, measure that that's root 2. From there to there is 2. From there to there is root 2. You form the product of the lengths of those 3 diagonals. Root 2 by root 2 is equal to 4. N equals 4. Unbelievable. N equals 5 is a little tricky. N equals 6, if you make this your reference point, the distance from there to there is 1. The distance from there to there is root 3. The distance from there to there is 2. The distance from there to there is root 3. Distance from there to there is 1. And when you form that product, 1 by root 3 by 2 by root 3 by 1, you wouldn't believe it, you get 6. So in other words, what you can do is you can, in conjunction with the students, you can verify that the product of the diagonals of a regular n-sided polygon is actually equal to n. It's something you can do with quite a bright middle school class as well, and taking it out of the guise of complex numbers. So I thought that that was a really nice thing to illustrate. All I've got here is this is where the roots and then the real parts and the imaginary parts, they're just housed in a spreadsheet. I haven't bothered to hide that. The next little demonstration is an alternative two-dimensional representation of the roots of unity. And to give you a little bit of background, I'll go to a Word document. And I wouldn't do it in this way with the students, but just to give you some background this evening, if you let z be equal to x plus yi, and we're considering the equation z cubed equals 1, by making that substitution, we can therefore say that x plus yi all cubed is equal to 1. What we can then do is we can take the real and the imaginary parts of both sides and basically form 2 equations. One which is saying the real part of z cubed equals 1, which in terms of x and y can be expressed as x times x squared minus 3y squared equals 1. And the imaginary part of z cubed equals 0. The reason why it's equal to 0 is because the right-hand side of the equation is 0i. You get 3x squared minus y squared all multiplied by y equals 0. And what you can do is you can plot the 2 curves, and where the 2 curves intersect are the 3 solutions, or in other words, the cube roots of unity. And I would say to the students, now think very carefully about this equation. What might it look like? And by using the null factor law, you can deduce that you should be able to see a y equals 0 or an x 0 or an x-axis part, and you should see 2 straight lines that are of the form, y equals plus or minus root 3x. This one's a little trickier to visualize. So moving back now to the Inspire. Here, now what I've done here, we've got our slider again. This is again a notes page. I very rarely work in the calculator page. This is also a new problem. I've built a wall between problem 1 and problem 2, so nothing that's in problem 1 will affect what's in problem 2. It's just it's variable management. And what I've done here is I have assigned 2 functions in terms of x and y, where in this instance n equals 3. So f of xy is the real part of x plus yi, in this instance cubed, and g of xy is the imaginary part of x plus yi cubed. Now, when we come to plot these 2 graphs, what we need to do is we need to move away from anything that involves complex number I. So what I've done here is I've assigned re. Now, this is also an interesting tactic that you may not be aware of, is you can assign equations. So I've assigned re to be f of xy equals 1. In other words, basically, this is the real part of z cubed equals 1. And when you press enter inside that math box, you get the output there, which is in green. And similarly, we do the same with the imaginary part. I've assigned m to be g of xy, set that equal to 0, and the equation that comes out is in green there. And what I'm going to do is, in using relation mode graphing, I'm going to exploit that ability to be able to graph re and m, and then look at the points of intersection of the two curves. The reason why I'm doing this is to give further consolidation to the visual aspect of complex roots, and in this instance, the nth roots of unity. And also by offering alternatives, hopefully, you know, improving students' you know, conceptual understanding of what's going on. May I say that if you are using the non-CAS version here, this is possible, but you would have to do the algebra by hand, which isn't too bad. I mean, you've got binomial theorem is your best friend here. And you can see that if you just change from n equals 3 to 4, you can see that you get updates. You know, for in this instance, this is the real part of z to the 5th equals 1. You know, and then the imaginary part of z to the 5th equals 0. So we go back to n equals 3, and we go to the next page, and again, this is just housing the various roots, real parts and imaginary parts, so I don't need to talk about that one. We go to the next page, and voila. In blue is the real curve, so this is the real part of z cubed equals 1, and in red is the imaginary part of z cubed equals 0. And I wasn't telling fibs. You can see that for the imaginary part, you've got the y equals 0, the x-axis involved, and you've also got these straight lines, y equals plus or minus root 3x, and then the blue line is the real part of z cubed equals 1. And you wouldn't believe it, they intersect in 3 points. And where they intersect are actually the solutions to the equation z cubed equals 1. In other words, the cube roots of unity. And what we can do now is we can just formalize this by pressing menu, and then we're going to go number 6 for analyze graph, number 4 for intersection. You may not have seen this before, but you can actually, there's my first corner, click, and then because first corner, and then click, second corner, click, and there's our first point of intersection. Notice -1/2 root 3 on 2, and we'll do it again. Menu, analyze graph intersection, first corner, second corner, and then we'll do it again. Menu, analyze graph intersection, first corner, second corner. Lovely. And what I'm going to do now is, so they're the cube roots of unity. Now I'm going to hide, so this is right click, so control menu, and hide the coordinates because I don't actually want them. And what we can do is we can join these up now by pressing menu, geometry, points and lines, segment, and then we go intersection point, intersection point, intersection point, intersection point, intersection point, intersection point. And that is an equilateral triangle, and the vertices are the cube roots of unity. Just to show you, if I now press Tab, here is the relation part of the graphing. All right, so to change the form of the graphing, you press Menu, Graph Entry, Edit, and then most of the time you're in function mode. I'm in relation mode here, so you press number 2. See how for relation number 1, I've used re, which I had assigned back on the notes page. And for the second relation, I had it assigned back on the notes page as im. And you can measure the side lengths, and you can measure the angle as well. Brian, I've got possibly 5 minutes, and then we can finish up. The two-dimensional representation only tells part of the story. That there is the XY plane. But what we can do actually is we can be even more clever, and we can exploit 3D graphing to visualize, in this instance, the cube roots of unity, or the nth roots of unity for any value of n. And all we would need to do is, if we plotted the graph of the surface of the mod of P of Z all squared, and look at where that surface touches the plane Z equals 0, of course the XY plane is where Z equals 0, then those touching points are going to also be relating to the roots of unity. So for example, if we consider P of Z to be Z cubed minus 1, and we then form P of Z, the mod of P of Z all squared, where Z equals X plus YI, if you don't have a CAS, the binomial theorem will be your friend there. That's the surface that you would need to plot if you were to visualize or to be able to see the cube roots of unity. So if we go back to Inspire, I've got a new problem. This now looks at the three-dimensional representation. And in machine language, I've basically assigned, this is our P of, this is the mod of P of Z all squared, where Z, basically we've got, it's P of Z is Z cubed minus 1. Here is our expanded expression in terms of X and Y. We could change this for values of n, and the great thing about the notes page is you get an updated result each time, so you can deal with many cases at once. And if we go to the next page, here I'm exploiting 3D graphing. So this reddish brown sheet, that's actually the plane Z equals 0, the XY plane. This is the graph of the surface. And back on the notes page, because I assigned Z of XY to be that, I've now assigned P to be Z of XY, so that when I come to graph, see how there I have graphed and I've used P, because it won't accept a complex number in that entry line. And you can see there are 3 points where that surface touches, makes contact with the XY plane. Those 3 places are the cube roots of unity. You can also say, well, how many touching places will there be for n equals 4? There's 4, there's 5, etc., etc. The other thing you can do is you can go and take the surface or the 3D graph on a bit of a hoon. So if you press Menu, Actions, number 8, you can put it sort of like on a rotisserie. You can put it on auto rotation, so you can get to see the 3 roots there. You can also change the value of n, while it's being rotated. And there's the n equals 5 case. Now it's difficult to see. You've got to press Escape to stop the auto rotation, which I'm trying to do. You can also manually rotate. You can do all this sort of stuff as well. blah, blah, blah. But what's really nice is here is a two-dimensional representation of this. So I've already prepared this, and there they are. And you wouldn't believe it, for n equals 5, so the fifth roots of unity, you've got 5 solutions. They form a regular pentagon. The angle, so for example, AED, I know I have it in radians, it's 1.88 radians. When you measure that in degrees, it comes out as 108 degrees, which makes sense. So the last thing I would do with the students is I would then get the navigator out and I would poll them with 5 questions, and you can send these one at a time or all at once. And so when n equals odd, there's always one root of the equation z to the n equals 1 located on the real axis of the complex plane. Is that true or false? The answer is true. The answer to this question, when n's even, there's always 2 roots of that equation located on the real axis of the complex plane. That's true. You get instant feedback on your teaching here. The roots of the equation z to the n equals 1 always lies on a circle of radius 1. That's true. The n roots are equally spaced around a circle. That's true. And the angle subtended at the center of the circle by consecutive roots of the equation z to the n equals 1 is 2 pi on n. So what I wanted to illustrate there, just with my brief time with you, is to show you that there are alternative ways of visualizing roots of complex numbers. And I also realize that a few of you may not teach complex numbers, but I wanted to show you some geometry tools and some graphing tools and some tactics with the notes application that you might be able to employ across the year levels in other topics and in other subjects, whereby you can produce really nice visual demonstrations for your students so that you can ask them really good questions and hopefully give them a good conceptual basis for what's going on. So what I showed you tonight is a little different to the way I learned it in 1984, and that's me done, Brian.
Thanks, Peter. Yes, I think both our presenters this evening showed us examples of certainly what emphasises the value of a visual for looking at these things. So we saw Peter's, where we can certainly do the algebra and the the crunching of the values for complex numbers, solutions. But I think once it becomes apparent on an Argand diagram, like the 2D representation, that's where it really comes together a bit better for me in teaching of specialist maths, and I know the students see that as well. I've never tried putting it into 3D, so that was interesting to see. When you were talking about the roots, I was wondering, one of the visuals there, I was just thinking a molar tooth, though, Peter. So I was wondering, was it the roots of a tooth? Maybe that's just my take on it. So thank you, Peter.
Thank you very much, Brian. Well done, Shelley. You did a good job.
Oh, thanks, Peter. You did too. That was really interesting.
So,
well, thank you very much.
Shelley also showing us the geometry, a lot of it, the circle geometry and plane geometry with our triangles and parallel lines and so forth. Good stuff for the early and middle years. And interestingly, there was a few references there along the way. I don't know if our participants noticed, but Shelley's calculator was the non-CAS version, and she was still able to do all that stuff. Peter's was the CAS version, computer algebra system on board, and referenced, as you said, that use of binomial theorem and with a little bit of extra calculus. Sorry, a little bit of extra algebra done manually. There's still access to the main part of those activities. So thank you to both of our presenters. I'm about to close the event. If you wish to use the chat panel to just throw in any last-minute questions. Now's your opportunity. I'm not going to answer them, but our two presenters will be monitoring that for you. Of course, you can always use that to also express your gratitude and accolades, and you can do more by filling in the feedback sheet on the page that you will be taken to in your web browser when I close the event. Within a couple of days, you'll be receiving a link to your certificate for attending this event, and that also links you through to the files, the backup files that our presenters are sharing for you and your students. If you want to see it all again, you can go to the on-demand section of our webinars. The link is there. I also typed it into the chat during the event. And I know a lot of students like to watch the webinars themselves, and they are also made available on our YouTube channel. Do you see the link there? YouTube.com, user TI Australia, or you Google that and you'll get it. If you're not already subscribed to the newsletter, I highly recommend you do. You not only get notifications of attending events such as these, but also face-to-face events, real ones where we have, well, this is real, but events where we can meet face-to-face at conferences, and also links through to other activities that are posted on our website regularly. Any further questions, please phone the numbers on your screen. One for Australia there, one for New Zealand. So, without any further ado, it's my duty now, and my very happy duty indeed, to thank both of our presenters, Shelley and Peter, and to all of our attendees. Thank you for joining us, and see you again.